Hello and welcome to this sixth session on atomic structure. So we're going to be looking at some extension material here, and in particular at the hydrogen emission spectrum. So this is the light emitted from excited hydrogen atoms. We can actually see the hydrogen emission spectrum at the bottom of the screen there. And this is significant historically because it's the best evidence that we have shells in the atom. And so the spectrum that we see below, this is the visible spectrum, and in this spectrum the wavelength is going to increase from left to right, which means the frequency and the energy increase from right to left. And so we can see, going from right to left there, you can see that the lines get bluer and they're getting closer together. So we get this convergence of the lines, which implies a convergence of the energy levels of the different shells in the hydrogen atom. And so, as it happens, this is the so-called Balmer series. And so what all these lines have in common is that in every case an electron is dropping down to the second shell from some higher shell. And in the picture we can see now on the screen, we've actually got the first three series shown on the diagram. You can see the green series at the top there. What all those transitions have in common is that the electron is dropping down to the first shell from higher shells. So you can see that as you go up to higher shells, the wavelength is getting shorter and shorter. This implies that the frequency and the energy are getting larger, as there's a bigger energy gap. So you can see the Balmer series there, that's dropping down to the second shell, as we were saying. And so the next one up is the Paschen series, where it's dropping, the electrons dropping down to the third shell. So what all these series have in common is that they all show convergence to a limit. Now, looking at this in a little bit more detail, in this particular diagram that we see up on the right hand side, we've actually got the energy levels of the different shells plotted to scale on an energy axis. So you can see on this diagram there is a very marked convergence. So you see the gap in energy between the first shell and the second shell is huge compared to the second shell and the third shell. In fact, the gap between the first and the second is bigger than the gap from n equals 2 up to the highest possible shell you could imagine. So looking up, the gaps get very, very much smaller, and they very quickly converge. And they converge to this limit. And you see that on the graph, that limit is actually described as having an energy of 0. So this 0 in energy is actually defined as the point at which the electron is really free from the nucleus. So this is the point where we ionize the electron off the atom. Now energy here, of course, we normally talk about energy in kilojoules per mole, but we have an alternative energy unit here, the electron volt. And we've got the equation as well in this picture that is the relationship between the energy and the shell number, n being the symbol for the shell number. So as I say, the convergence of the levels is very clear here in this picture. There we go. And so this thing about the 0 being defined at the top does mean that all the other energies are defined as negative. It seems a bit weird, negative energy, but in a sense these energies, it's all just kind of arbitrary what we make them relative to. Sometimes you see energy measured relative to the ground state, but in this particular case we've got energy relative to the ionization limit. And now looking again at these transitions in a bit more detail, we see again these series of transitions on the right hand side, and in this diagram we've also got the bracket series, where what they have in common, the level to which the electron is always dropping here, is the fourth level. So when we record a hydrogen atomic emission spectrum, we see actually all the possible transitions taking place. And so essentially what we do, so you might start off with hydrogen molecules, but in a discharge, high voltage discharge tube, the molecules will be broken down to atoms, and then they'll be ionized. And so the free electrons, then they'll return back to the nuclei. Ultimately they'll return back to the ground state in the first shell, but they'll typically get there via certain intermediary levels. And so in fact the electron can access all the possible levels. So once you consider all the atoms together, ultimately you're going to see the transitions between all the possible energy levels. And that's why in the spectrum of a sample of gas we can actually see every possible transition. But we have to bear in mind, of course, that most of these are not in the visible part of the spectrum. So you see that only the Balmer series there, dropping down to n=2, only that's actually visible to us. Passion and Brackett and higher series, these will be in the infrared at lower energy, and the Lyman series will be in the ultraviolet to higher energy. And then we meet this important relation here that the frequency of the line is directly proportional to the energy of the transition, the energy of the photon. And it's this classic equation E=hf, energy equals this constant of proportionality, which is the Planck constant, the fundamental constant, multiplied by the frequency. So when we start doing calculations with atomic spectroscopy, there are really three important equations, and it's these equations on the screen here. E=hf, which I just mentioned. This is the relationship between, if you like, the energy of a photon and the frequency of a photon. Then we've got C=f lambda, c being the speed of light, f being the frequency, lambda being the wavelength. So this is a general thing for any wave. And then finally this En equation. So that's the energy of an electron as a function of the shell number n being equal to minus. So again, that's that minus that we saw before. We define all the shell energies as negative, because remember we've got 0 defined as the limit. R being a constant that we're calling the Rydberg, divided by n squared, n being the shell number. So I think beneath those three equations, I've just summarized there what all these different quantities are, and I've got the exact values here of the Planck constant and the speed of light. So the Planck constant really kind of characterizes the size of these fundamental units that we consider. That's why it's such a small number. So these tiny quantum objects like photons. Now there's some exercises to think about. So you might like to stop the video at various places and have a think about it. So this first question here relates to the fact that the Rydberg constant is the ionization energy for hydrogen. So that was 1312 kilojoules per mole. And so the question here is, what would be the ionization energy for a single atom? So it's really converting between a molar quantity and a single atom, which is going to require Avogadro's constant there. So that should hopefully be fairly straightforward. So next question, working out the frequency of radiation that will just ionize a hydrogen atom. So you see, we're going to be using the energy for a hydrogen atom from the first question and converting that energy into a frequency. So hopefully you remember the equation that's got E and F in it that we can use to convert between them. So our next question here is working out the wavelength of that radiation that just ionizes a hydrogen atom. So again, we've got the frequency F, and hopefully you remember the equation that's got frequency and lambda for wavelength in it, so we can convert between the two. And then next up we've got the energy of an electron in the second shell of a hydrogen atom. So this is that equation which is the energy of an electron as a function of the shell number that we looked at on the previous slide. And now the energy in kilojoules per mole of a transition from the third to the second shell. So this is going to be the difference in energy between two levels, n=3 and n=2. So again, it's going to involve that energy equation, but this time it's the difference between two values. And now going on to the answers for these questions. So in the first question we had 1312 kilojoules per mole as the ionization energy for a hydrogen atom, and we've got to remember to convert kilojoules to joules. So I've multiplied by 1,000 here to get a value in joules per mole, and then when I divide that by Avogadro's number, which really has the units of per mole, the number of things in a mole, that gives us the value for one hydrogen atom. So you can see it's an extremely small energy for one hydrogen atom. Not surprising really, as there are so many atoms in a mole. Then on to the second question, we were asked to convert that energy into a frequency. So this was the E=hf equation, making f the subject, E/h E being the answer from the last question, h being the Planck's constant. And so there we have the frequency in hertz of that radiation, the radiation that corresponds to the ionization. Of course, the ionization involves going from the first shell up to the limit, if you like, the infinitieth shell. So this is one of the Lyman transitions, isn't it? And so this is going to be in the ultraviolet. So that frequency of light there will be an ultraviolet frequency. And then in the next question, we were converting that frequency to a wavelength. That was the c equals f lambda equation, c the speed of light, f frequency, lambda wavelength. So we make lambda the subject, then we put the speed of light in there for c and divide that by the frequency we found in the previous question, and this comes out to the wavelength, which drops out in meters as the standard unit. And if we convert that to nanometers, we see it's this very short frequency there, under 100 nanometers. So you need to get up to about 400 nanometers before you're seeing it. So it's a higher frequency than visible light, so we're in the ultraviolet. So the next question now was about the energy of the electron in the second shell. So this is substituting in n equals 2 to that energy equation for each shell. So it's minus the Rydberg constant, the ionization energy for hydrogen, divided by 2 squared. So that's a quarter of the Rydberg constant with a minus sign in front of it. So that gives us this negative energy for that electron in the second shell. So negative converted, negative relative to the ionization limit. And so then this final question was the difference in energy between the third and the second shell. So I've got in here the energy in the third shell minus r over 3 squared, subtracting them from that the negative, so the energy in the second shell minus r over 2 squared. And so because the units of r were in kilojoules per mole, our answer comes out there in kilojoules per mole. And now on to a few more questions. So same thing, you can stop the video and have a think about these questions a bit more. And so looking in a bit more detail at the emission spectrum of hydrogen. So as I said, we're actually seeing all possible transitions between shells here and emission going down in energy. So our first question here, between which two shells is the lowest energy transition in the Lyman series? So you have to remember how we define the Lyman series to answer this one. Then we're calculating the energy of this transition in kilojoules per mole. It's a bit like the previous question we did. It's going to be the difference between two energies. So it's that energy as a function of n equation. Now the frequency of light corresponding to that transition. So again, converting from energy to frequency. Remember the equation that does that. Same as before, now looking at the wavelength of light this corresponds to. So we're using the equation that connects frequency and wavelength. And finally, how can the ionization energy for the hydrogen atom be estimated from the Lyman series? So as long as you remember what the ionization energy means and you remember what the Lyman series is, it should hopefully be fairly straightforward. And now finally looking at the answers. So our Lyman series was defined as all of the transitions down to the first shell. So the lowest energy transition will be from the nearest shell to the first shell. So it's dropping from the second shell down to the first shell. That's our lowest energy transition in the Lyman series. And then it asks, what is the energy of this transition? So this is the difference between two energies, the energy of the electron in the second shell, the energy of the electron in the first shell. So I've just substituted that in to our energy as a function of n equation, the minus r over n squared. So that comes out as 3/4 of the Rydberg, so nearly 1,000 kilojoules per mole there. And so we're now converting that energy into a frequency. So to do this, because we had kilojoules per mole as our energy, we can first convert that into joules per mole, multiplying by 1,000, and then we need to convert it to the individual atoms. So this E equals HF equation we're using, this is for, if you like, a single photon for a single atom. So we divide by 6 times 10 to the 23, the Avogadro's constant, to give us the energy for a single atom. Then we divide that by Planck's constant to give us the frequency. So now we're asked for the wavelength, so using our C equals F lambda equation, make lambda the subject. So we put in the speed of light, divide it by the frequency that we just got in the last question, and then out comes our wavelength. So again, we see this is in the ultraviolet part of the spectrum, it's under 400 nanometers. And then finally, how we find the ionization energy. Well, the ionization energy is going from the electron in the ground state all the way up to the limit, up to 0, which is like the infinitieth shell. And so in fact, what that means is, because it's the convergence limit, we would have a look at the line spectrum, we would estimate where the lines are converging to. And so that final line at the highest energy at the convergence limit, that would correspond to the ionization energy.